Good afternoon. This is Kyle Welch with RCR Wireless News. Welcome to today's webinar, presented by Azimuth Systems. Accelerate device excellence, advancements in mobile performance testing from lab to field. Our presenters today are Amit Malhotra, Vice President of Marketing and Product Management at Azimuth Systems, and Deepak Das, Vice President of Software and Solutions at Azimuth Systems. Just a note to all of the attendees today, within 24 hours of this webinar, we will provide you with a link to the on-demand version of today's webinar. During the webinar, we encourage you to submit any questions you may have, which will be answered towards the end of the presentation. Without any farther ado, I'm going to hand the webinar over to Amit and Deepak. Guys, take it away.
Thanks very much, Kyle, and welcome everyone. As Kyle said, my name is Amit Malhotra, Vice President of Marketing and Product Management at Azimuth. And with me here today is Deepak Das, Vice President of Software and Solutions.
Hello, everyone.
Azimuth is a provider of mobile performance test systems, counting the industry's leading operators, OEMs, chipset vendors, and infrastructure vendors among our customers. Today, Deepak and I would like to provide you with Azimuth's perspective on mobile performance testing and where that testing needs to evolve to address the industry's current challenges. But before we really get started, a friend of mine in the industry once told me the beginning of wisdom is the definition of terms. So what exactly do we mean by accelerating device excellence? Well, specifically, we're going to focus today on the substantial amount of testing that takes place in the area of mobile user experience, centered on the device or user equipment. So accelerating device excellence is really about minimizing the time required to prove new mobile user equipment will delight subscribers or to fix issues found once user equipment is in market. So what we'll be covering will be the evolution of mobile performance test, and then two critical stages of that testing. First, in the lab, and we'll be looking at advancements in field playback as well as over-the-air platforms. Then we're going to be looking at the complementary testing in the field, or the live network. And there we're going to be looking at device automation and diagnostics and analytics. We'll bring that together across the lab, across the field, and very importantly, across ecosystem partners to show you how all these organizations can work together more effectively during mobile testing. And that really is the key to accelerating device excellence. Then we'll open it up to Q&A. And as I understand it, we might be getting questions along the way, and Kyle will be feeding those to us at opportune moments. So let's talk a little bit about mobile performance evolution, or mobile performance test evolution, starting with yesterday. Remember those days with fewer network technologies, fewer frequency bands, fewer types of devices? I still remember walking into my first network operator retail store, where the entire store was centered on providing a choice between two black phones that did voice only. In those days, and until fairly recently, given the life of our industry, testing was much more static and could be done using statistical channel models. Now let's look at how mobile performance and hence testing has evolved to today. Each of those dimensions that I just spoke about, including network technologies and devices, has mushroomed in complexity. You have multiple network technologies that are delivered with different nuances, whether MIMO, carrier aggregation, HETNET. The devices themselves, which now contain much of the resources and intelligence to influence the user experience. One of my favorite quotes is the fact that the typical smartphone today has more processing power than NASA had to send the first man to the moon. But beyond just the devices, you have over-the-top applications, which are replacing core device functions. And each of these levels is successively one step further from the operator's realm of control. And as a result, the mobile environment is extraordinarily dynamic and unpredictable. So not something that can be easily modeled at all. As a result of that, operators, OEMs, chipset vendors, infrastructure vendors, the entire ecosystem around devices is spending a substantial amount of time and money on testing across various phases, including R&D, conformance, performance, both in the lab and the field, all the way through launch and post-launch. And some estimates are that the amount of testing on an annual basis adds up to about $1.6 billion. And pretty interestingly, of that, a substantial amount, around 300 million, is taking place post-launch, because as much testing as occurs before a device is launched into market, there are always issues found. And interestingly enough, up to half of devices returned to operators are found to have no troubles. And that's something that the industry is trying to do a lot more testing on, both post-launch as well as driving more effective testing pre-launch to minimize that cost. In addition to network or technology challenges, the industry is going through a lot of operational challenges on the testing side. So there is competitive pressure to minimize time to market and resolve issues, which inherently calls for faster correlation between all of the entities investigating issues, including the lab, the field, the network, the ecosystem partners. There's increased scope of testing from all of those additional complexities, which is generating gigabytes worth of data every hour, which is getting harder to store and harder to warehouse and analyze. So there's a tremendous store of information that currently is being significantly underutilized at every level. And finally, limited budgets. So with all of that complexity and increased requirements for testing, does not often come the commensurate budget. And so operators, OEMs, and their ecosystems are continually being forced to do more with the same resources, or sometimes even less. So in terms of the current state of the test tools available to the industry, they're inadequate because, first of all, there's little or no feedback among the functional silos. They all have their own set of tools that they've been using traditionally. They, especially in the lab, have a very difficult time replicating the real-world environment, and are often insufficient for newer types of network technologies. So what Azimuth would like to share is, what we see as the principles of mobile performance test evolved. First of all, with underlying technologies growing in complexity, tracking the user experience in real-world environments becomes ever more critical. Basically, no matter how the factors underpinning the user experience evolve, the service provider and its ecosystem must keep a laser focus on measuring that experience as close as possible to the way subscribers undergo it. That's really the only way to make sure that subscriber satisfaction is maximized. At the same time, you have to adopt an end-to-end approach with device performance as the focus. So device performance is the proxy for user experience when an issue arises. It's essential to be able to trace it to a root cause across the application, the device, the channel, or the network. So having that end-to-end focus across that entire chain is critical. And then you have to closely scrutinize the device network interaction, because as much as subscriber satisfaction is a key focus, so too is minimizing the impact on the network, particularly with the increasing amount of complex applications that are continually being added to devices, and the increasing amount of uncertainty as to how they will impact the network once they're out in the wild. It's also very critical to harmonize field and lab testing, because with all the competitive pressures, there's less and less time for translation of findings from one environment to the other, and less budget for disparate tool sets. And finally, it's really important to use test methodologies designed for complex devices. So everyone needs to update test cases for new scenarios. For example, VoLTE, whereas user experience used to primarily revolve around voice quality and call performance, now it has to also include delay, jitter, and seamless handoff between different radio access technologies. So what that translates to for us is the end-to-end mobile performance test paradigm, which I'd like to share with you here. Starting with the user experience, including core and emerging applications, which together are really driving the user experience and subscriber satisfaction. Everything from voice, messaging, data, all the way through to emerging applications, including video streaming and rich communication services. Harmonization of testing frameworks across the lab, which is here represented by the emulated network, as well as the field, which is represented by the live network. Brought together by end-to-end analysis from applications to the device to the network, and all captured in a database that can be analyzed over time and shared into the ecosystem. So what I'm going to do now is take us through some of these environments and then pull all of this together at the end, so you can see how the pieces of the puzzle really fit together. So first of all, accelerating device excellence in the lab. Historically, the lab environment has emulated the live network, starting with conducted testing based on standard channel models. Over time, the objective has been to emulate the network closer and closer to real-world conditions, accepting that 100% correlation would never be possible. So, starting with conducted testing with standard channel models, there's been an evolution to introduce over-the-air testing, also using standard channel models. And what that does is it increases the effectiveness of testing the device, because instead of simply conducted, now you're also exercising the antenna the way a subscriber would in the real world. But it's still using standard channel models. Then another stage in the evolution has been conducted testing using real drive logs. So instead of just simulating standard models, you're actually simulating a real drive route, which we'll talk about in a little bit. And then beyond that is over-the-air testing with real drive logs. So that basically is exercising the device in its natural state, and in an environment that is closer to what subscribers will experience out in the real world. And what we're going to spend some time on in this section is improvements in field playback, or using real drive logs, as well as over-the-air testing. So something that's been around for a while in the industry field playback or field to lab. I'm just going to provide a bit of a refresher here. But essentially, a field test van with test devices and either hardware or software scanners, which will survey the network conditions, will be driving down a route that typically is used for testing by an operator or an OEM, and collecting measurements of network conditions and specific messages that you see here along that route. Those logs are then brought into the lab and processed, filtered, mapped to the available sectors in the lab environment, and then fed back to devices through a channel emulator, and therefore providing the devices with network information similar to what they would receive out in the real world. And that can be then replayed over and over again. So that is a technology that has been in test and measurement for a couple of years now, and has been extraordinarily successful at helping testers in the lab to replicate conditions in the field without necessarily having to expend resources in the field. So now I'm going to turn it over to Deepak, who's going to talk about one of the enhancements in field to lab, specifically with respect to reciprocal path loss.
Hello, everyone. So as Amit just summarized, for field to lab, the underlying concept is to recreate as much as possible the field conditions that the device experienced out in a field test back in the lab. And the focus of this discussion is more on reproduction of the RF conditions. And typically, a lot of the focus has been on the downlink. As most of us are aware, in our own usage of devices, we so far, a lot of the applications rely on downlink data transfers. But increasingly, the focus is turning towards uplink testing, and because as again all of us are aware, a lot of applications are now resulting in data uploads back into the network. So when we try to evolve field to lab, as we knew centered around downlink testing, to uplink, one of the first places to look at is the path loss, which essentially captures the degradation of signal experiences in getting from the device back to the base station or the access point. And the feature that I'm going to focus on in the next few slides is reciprocal path loss. Both for FDD and TDD systems, typically the macro statistics such as path loss are expected to track on the downlink and the uplink. And further, in TDD systems, other aspects of the channel such as power delay profile and even spatial characteristics are expected to again be similar between uplink and downlink. So to go back to one of the tenets that Amit pointed out in device excellence testing is to harmonize field and lab. And in that spirit, it becomes more and more important to make sure that not only the downlink but also the uplink is closer to what the device and the network experienced in the field. So before I dive into an example of how reverse link reciprocal path loss helps isolate some issues, here's a list of user behavior areas that clearly are affected by reverse link performance as much as downlink. And to quickly go over these different areas, clearly reverse link, capturing the reverse link artifacts realistically in the lab affects testing around connectivity, like call failures, call drops, handoff performance, mobility, which are influenced by measurement reports, and also the signaling that needs to occur for handovers. Clearly throughput, especially like I said, uplink throughput, that is sort of the underpinning for a lot of applications that are trying to upload data into the network. Battery life, a device's battery life is significantly influenced by its transmit power, which controls the fidelity of its uplink transmissions. And in some cases, especially for TDD, there is room for advanced LTE algorithms centered around multi-user beamforming, where the uplink measurements are used to figure out the appropriate downlink scheduling for different users. And finally, link adaptation methods such as power control, rate control, these are clearly influenced by mimicking the reverse link realistically in the lab as seen in the field. So to underscore the importance of this particular feature, reciprocal path loss, we ran a simple test with which is an uplink throughput test using FTP as the application on a 3G femtocell. And we ran the test twice, once with the reciprocal path loss, where the path loss, like I described, on the reverse link mimics that on the forward link. And the other case, we used what we call an uplink box, which essentially sets a certain level of fixed path loss and runs the whole test with this arbitrarily fixed path loss. What we find is very interesting. In the top chart, you will see the blue line that captures the throughput performance we see with the reciprocal path loss in action. And the red line, significantly different in behavior, captures what happens when we don't have reciprocal path loss and instead have a fixed and arbitrary path loss. So to understand the results, let me describe what we expect. So this is a 3G femtocell in a lab environment, and it's a pretty clean channel. The backhaul, which is the connection to the internet, is enterprise grade. So, and the kind of channel we're trying to play back on the downlink, we expect that the femtocell with just one device connected to it should be able to maintain a pretty good throughput. And that's what we see with the reverse link path loss. A throughput of reverse link throughput file layer is of about 1.2 Mbps in maintained throughout the test. And that matches our expectations. What we see with the fixed arbitrary reverse link path loss is a little counterintuitive. We see that the throughput is pretty low in the beginning, and then it shoots up and has a performance and a behavior that is significantly different than what we expected. And the reason behind that is because in 3G, this is a EVDO femtocell. The power control on the uplink is a function of both open loop and closed loop power control. And the UE, in response to the downlink channel variations captured in the playback, is responding by increasing its TX power when the uplink channel is weak, when the downlink channel that we're playing back is weak, and decreasing its TX power when the downlink channel that we are playing back is strong. What that means is that the base station is now seeing much stronger, because the path loss is fixed in the uplink box case, which is the fixed path loss case. The base station sees highly fluctuating received power, and when the UE is actually transmitting much higher power, the base station responds by setting what is called the reverse activity bit, which essentially the base station senses a lot of loading. And so artificially, because of having chosen an arbitrary but fixed and somewhat low reverse link path loss, the base station is responding by actually throttling the throughput when the UE is actually transmitting more power. So this is an artifact that is not seen in a real test. The real test is more closer to what we see with the blue line, which is reverse link path loss. So in summary, reciprocal path loss ensures that the appropriate amount of loading is perceived at the base station due to the transmission on the uplink by the device.
Thanks very much, Deepak. So now, having looked at one advancement with field to lab or field playback in the lab, I'm going to now take us to another environment in the lab. So we've gone from field to lab, which we've been discussing, is primarily a conducted type of testing, which means specifically that there's cables from a channel emulator to the device to over the air with field playback. So the same paradigm that we've been talking about so far, which includes replaying real drive route logs in the lab, but instead of the final connection to the device being via cable, it's now over the air. So it's also exercising the antenna. And this is a type of testing that's also been around for a couple of years, but has not been used extensively with field playback. And what we're talking about now is really combining the power of those two different types of testing. First of all, what I'd like to share with you before we talk about over-the-air with field playback is over-the-air itself. So if you've got an over-the-air chamber in the lab being used for performance testing, what kind of benefit does that really provide? Well, what we see here is a real-world example. These are results from a lab outside of Azimuth using the Azimuth OTA platform with standard channel models to benchmark throughput of 7 devices. And the two different channel models are urban macro and urban micro. As you can see, there's a significant spread in the performance. So for a specified RS EPRI, throughput varied by up to 500%. And some devices did better in the more challenging urban macro model than the urban micro, or others did in the urban micro. So what we've been told by the operator of this lab is that this lab testing using over-the-air provided them with much better predictability of how these devices would perform in the field compared to the testing they've been doing previously. So over-the-air does represent a significant advancement towards getting closer to real-world conditions. But now, when we actually feed real drive logs into the over-the-air system rather than the standard channel models, we see an even more dramatic improvement. So first of all, what you see here is downlink physical air throughput measured for 3 devices that are commercially available on a live network. So these are field measurements, and you can see over the course of the drive across 25 download iterations for the 3 devices, what the performance was along that drive route. When we replay that drive route in the lab with over-the-air testing, what we find is while the correlation is not 100%, and that's something that we've talked about earlier, the actual relative ranking of device performance is pretty close to what we observed in the field. And so this type of testing, where you're using over-the-air with field playback, is an even better predictor of device performance in the field compared to either over-the-air using standard channel models or field playback with conducted testing. So with that, couple of different views of advancements of mobile performance testing in the lab, we're now going to transition to the field environment. And I'm going to turn it over to Deepak again so that he can talk about specific advancements in device automation and diagnostics and analytics.
So to start this part of the discussion, let's review some of the tenets that Amit had outlined as part of the device testing evolution. So the aim is to focus on end user experience as a starting point, and specifically capture the end user experience through metrics that are based on applications that the end user is running, such as popular video streaming applications, web downloads, and change the focus more towards these applications that the user typically uses rather than legacy style FTP full buffer kind of testing. So focus on end user experience and then tie it in an efficient and integrated way to the underlying device network interaction. So it is important to make sure that for the same application in an apples to apples comparison across two phones, to answer questions such as, did one phone make more connections than the other phone with the network? Did one phone had more of a signal chatter with the network than the other phone? And to be able to study user experience and link it efficiently done device testing in the field, you realize that one good way to debug issues or characterize performance is using the benchmarking paradigm. So this example that I'm going to walk through very quickly is one where we are trying to benchmark two devices and trying to debug and isolate root cause for some differences that we see between two devices. And again, going back to one of the earlier tenets, it is important in the new device testing paradigm to have an end-to-end approach. A siloed look at each at different aspects is useful for first level debugging, but eventually by the time the device is performing in the field and one is trying to explain its performance in the field, it is almost necessary to have an end-to-end approach to testing. And last but not the least, it is important to make sure that the paradigm or the framework for testing in the field is harmonized with that of the lab. So field to lab is an example where, at least on the RF side, the testing has been harmonized between field and lab. Similarly, for device automation, diagnostics, it is important to have a harmonized framework for field and lab testing. So in the sample use case that you see on this slide, I'm going to focus on user perceived throughput benchmarking. And so we have a test device and a reference device. And the applications that we tested in this example are FTP, HTTP video streaming. In the interest of time, we are going to focus on the results pertaining to FTP, but some of the conclusions we drew for FTP were also true for HTTP and video streaming on these two phones. And the focus here through the next few slides is to understand how user experience has to be connected to underlying device network interaction. So our starting point is our Azimuth device automation solution which we use to run these applications on a device under test, which is a new phone, simultaneously with a reference device, so that we can create the right data for an apples-to-apples comparison. And once we have all the logs collected from the device automation solution, we feed it into our Azimuth diagnostic tool to isolate where the issues might be that explain the difference in performance. So before we get into the specific results, this is a flow chart that is familiar to a lot of testers and system engineers whose charter is to debug issues seen in the field or in the lab. And people have different versions of it, but bottom line, it's a systematic way to look at diagnostics and try to isolate root cause. A good starting point for any wireless debugging exercise is to start with the RF. And so the first step, you need to make sure that the RF conditions were comparable. Once that is established, you need to understand whether, given those RF conditions, did both the devices report the same channel quality. And once that is understood, to look at, okay, what is the 5-layer burst rate that they both got. burst rate here is throughput of experienced by the device when it was actually being served by the base station. So once at each of these stages, if the answer is no, then there are specific areas to look at. So for example, if the 5-layer burst rate is not comparable, good areas to look at to understand why one device is different from the other in its performance is MIMO rank, downlink MCS, downlink block error rate, MAC 5-layer features such as HARQ, resource block allocation, etc. Beyond these steps, then one needs to understand each area in more detail, and the flowchart here is trying to capture how, starting with user experience, one can quickly follow systematic steps and having an end-to-end approach through all the protocol layers, all the way up to IP and TCP, to understand where the root cause the issues that explain the differences between two phones. So in this example test that we ran with FTP, HTTP, and video streaming, these are the results for FTP, and we see that clearly the test device over multiple iterations does worse than the reference device. So the device automation solution is very instrumental in providing this quick snapshot of user experience, because this is closest to what the user would have experienced through the application that was using the FTP mechanism to do its data transfer. So starting with user experience, we then peek underneath at the different layers, and through the diagnostic tool, we have here a snapshot of one area where we start seeing a difference between the test device and the reference device. And that, given that the RF conditions on both the devices, as captured by RSRP, RSRQ, RSSI, SNR, are comparable, we see that there is significant degradation in the test device physical layer burst rate as compared to the reference device. So having identified that, we then try to figure out what could be causing this 5-layer burst rate difference. And so the next step is to look at the fundamental underpinning of 4G technology, which is MIMO behavior. And what we see is that the test device actually operated at a much lower rank compared to the reference device. So although we ensured through device automation that both devices ran the same tests under almost the same conditions at the same time, the performance of one device versus the other in terms of 5-layer burst rate was significantly different. And to explain that further, through the diagnostic and the analysis tool, we were able to isolate that the average rank requested by the UE in the test device was lower than the reference device. So in summary, what this exercise, sort of to reiterate what it showed, was that in device testing, and to understand performance and characterize it and debug it, we need to have focus on a good starting point is end user experience. Then we need to tie it to underlying device network interaction, have a end-to-end view of across protocol layers and application, and finally have a harmonized framework between field and lab testing, such that field testing can be reproduced in the lab using the same framework.
Thanks very much, Deepak. All right, so we've just taken a trip through mobile performance test lab and then mobile performance test field team, and explored some advancements in each area that are helping organizations from operators to OEMs and their ecosystems really test more effectively. But I think what's as important as what's happening in each of those environments is how they can work together. And so what I'm going to take a few minutes to talk about now is accelerating device excellence across the lab, the field, and into the ecosystem partners. So to begin with, whereas at one point in time there might have been testing taking place in a lab, which is the second layer you see here, and separately very important to do now, and what is very possible to do now, is to harmonize those test paradigms. First, by having a test HQ, or a reporting and administration center within the testing organization, which builds a test plan that can be deployed across all of these environments, so that devices under test are undergoing the same conditions, including the types of applications and the number of iterations that are being run on those devices, the types of conditions that they're being put through. That test plan then is relayed down to the lab, which can download the test plan and then run that test plan on the emulated network, whether that's conducted over the air or over the air with field playback. It's also run separately, but in a coordinated manner in the field. So you've got an example here of a couple of different markets, geographic markets that might be testing those devices. And then in each of those environments, the results can be analyzed locally, but very importantly, then uploaded to a central store to ensure cohesive treatment of all results and warehousing so that they can be analyzed over time. One of the most important aspects of quality assurance in mobile devices is to be able to test against expectations based on what historical experience has been. So it's extremely important to maintain that database so that future devices can be measured against historical experience, and improvement expectations can also be set against that experience. If that's done effectively, then what the industry has is a very efficient and sophisticated mobile performance feedback loop. So starting with the lab, where we've just spent some time looking at testing of devices using device automation together with field playback over the air, and then transferring those findings to the field, so that rather than doing purely independent testing, the field is sharing information from the lab using the same tool sets such as device automation, so that they can ensure a commonality of methodology as well as results framework. But using device automation now, rather than in an emulated environment, using it on the live network. And then analytics from there are transferred over to the post-launch environment. So once the device actually goes into market, and whether you're talking about supply chain that is receiving returned devices, or you're talking about network teams that are investigating issues that have been reported in the field with devices already in market, they have the ability to track back to previous testing that was done, and then use, again, common tool sets such as device automation, field playback over the air, this time after the device has been launched in market. And then for the current generation of devices, that experience and information can then be transferred into device R&D, so that the next generation of devices is informed by the experience that occurred previously, and then that cycle starts over again with pre-launch testing on that generation of devices. So that wraps up our webinar with a view of the testing that's taking place in the lab, in the field, bringing it together between the lab and the field into the ecosystem in this mobile performance feedback loop that's now not just possible, but it's essential to ensure that devices can get to market faster with quality that will ensure subscriber satisfaction. With that, I'm going to turn it back to Kyle and open it up for questions and answers.
Thanks, Malhotra and Deepak. So yeah, we have a couple questions we got in during your presentation, and I encourage all of our listeners to submit their questions under the question panel. The first one coming in is, can you guys take a little time and comment on how the testing paradigm addresses what operators are experiencing in terms of user device returns?
Sure. Deepak, do you want to take a shot at that? Or?
Yes. So as Amit pointed out, a lot of the device returns, a very significant number are traced back to no fault found, and that is an area of great concern to operators. And our belief is, and this is shared by some of our industry partners, is that a lot of the testing that these devices went through and they were not flagged as faulty devices were one siloed, and so there was R&D testing and then pre-launch, post-launch with not too much feedback between these different testing phases. And second, the testing in the lab was not necessarily as realistic. It was more legacy style, channel models based, standard channel model based. And so these are two of the areas that they agree with us in understanding that we need to make the testing more realistic in the lab to be able to predict and catch issues that are seen in the field.
Yeah, and this is Amit. I'll say that it would be very useful to reverse logistics, for example, when they're processing returns, to have some visibility into the testing that occurred previously, and that's pretty challenging to do when different organizations are using different types of test methodologies and are not sharing results. So really the paradigm we've talked about is to ensure that that information is available across the entire product lifecycle, so that different parts of the organization can make good business decisions.
Thanks, guys. We have one more question that just came in, and it's asking if you guys can comment on how you guys expect the testing to evolve with LTE advanced deployments.
Deepak, you want to take that one?
Yes. So we in the spirit of making testing more real, with LTE Advanced, there is significant amount of work that is being discussed in the standards and in LTE towards aggregating and using resources better in the network. So as we pointed out, devices are getting very complex, and so is the network. And LTE Advanced is replete with features where network nodes are collaborating with each other through features such as EICIC, which is enhanced interference control mechanisms, through aggregation of spectrum like carrier aggregation, and then the host of changes that are being put in place to accommodate heterogeneous network deployments, where small cells, picocells, femtocells have to coexist with macro cell deployment. So device testing in its evolution has to evolve to keep some of that, keep that whole evolution in mind. And the way to do that is in the same spirit, to make sure that testing done in the lab for these advanced features are reflective of what the device is going to see in the field, which is going to get even more and more complex. And further, in terms of the diagnostics, there are developments in the standards which are very encouraging. One of them is this effort called minimization of drive test, MDT, and the devices via this feature are required to actually collect more and more information about when certain things happened in the network. And once devices start implementing these kind of features, I think that's another area that can be leveraged to quickly to put in frameworks and solutions and systems that can quickly help resolution of issues.
Thanks, Deepak. We had one more question come in, and as the industry may need a unified and repeatable testing method, who and how and who is defining, unifying, and authorizing these testing methods?
So that is actually a great question. And one of the things that we're seeing is essentially that while there are some very significant standards bodies, everybody from CTIA to 3GPP and others, um, their ability to deploy standards is currently being outstripped by the rapid evolution of technologies. So, you know, the way that I think even the operators, OEMs are struggling with the onslaught of new technologies. For example, I don't think we would have predicted, just a few years ago, how much of an impact different types of applications are having on the user experience and the network. Um, in the same vein, there are all kinds of network technologies, device technologies, and service technologies that are being deployed pretty rapidly that the standards bodies are struggling with. So where we see a lot of the focus of that unified testing is actually at the operator level, especially in the United States, because it's here in the U.S. that the operators provide the devices to subscribers and are most closely associated with user experience, even if the issue may have nothing to do with what they're providing. And so, we've been working with a number of operators who are really at the forefront of trying to really drive that unified testing. And we're seeing some pretty dramatic results through that process.
Okay, thank you. That about does it for our time today. I just want to thank both Amit Malhotra and Deepak Das from Azimuth Systems for joining us. Just a reminder to the audience that we will email out on-demand version of this webinar for your reference. And if you have any questions, feel free to email us. And thank you, guys.
Thank you very much.
Thanks, Kyle.
Thanks.